Hello there. In this video we're going to talk about binary search trees. We sort of skipped past a few other things, but it is time to talk about binary search trees. We'll start with just a quick review of what we did in class that didn't show up in a video, and a few notes on this, and then the point is to look at the code. Okay, so a binary search tree is a data structure to keep some information, and we have the picture here. Let's go ahead with okay, well, good enough. So here we have a picture of a binary search tree. So we have some information that we're going to keep inside of this box here. Here we have words of, and, all, ball, arc, and the. And the basic unit of a binary search tree is a node. The node has data inside of it. It looks like we have counts as well. There's of and the number 5. That's the same as one of our previous examples here. Alright, so there we have of and the number 5. That's the data of the node, and then each node has a left pointer and a right pointer. The rule is that everything to your left is going to be either bigger or smaller. Which one is it? It's smaller. This is a decision that we make as designing this data structure. So everything that goes through this left pointer is going to be smaller than of in terms of alphabetical order. So if we go to the next one, we could have something there so there's some data there, and then we have a left pointer and a right pointer, and the rule is that anything that's to the left of this has to be smaller than and. All is smaller than and. Anything to the right of and needs to be larger than and, but also smaller than of. Okay, and so on. All right, so that is the binary search tree. The basic element there is a node. Put some notes here. So the node is the basic element. You can read that. And then the rule is that everything to the left is smaller, everything to the right is larger. We can go ahead here and put a new one in. So let's just say that we are going to put in something new, call it cat, with a number of, who knows, maybe 6. Okay, so that would be, let's draw a box. So we'd have some box here, and we would want to put this in. So we go to the insert operation, which we did in class. So we have to compare this against the root if we're going to put it in. So is it less than or bigger than the root? It's less than, so we go to the left. Now we're comparing it against and. That's the one that's just to the left of the root. Cat is bigger than and, so we would go to the next one, which is ball. Sorry, to the right of and. Cat is bigger than ball, so we'd go to the right of ball. Looks like here we had already inserted something that would be to the right of ball, so we go and check against that. And there's fast, so we would go to the left of fast, and right now there isn't anything there, so this would be time to put it in. So we'd have the left pointer of fast would now go to our new item, cat. Alright, so that's the insert. Basic algorithm is we try to find where we would put this by going left and right, and eventually we come to a point where there's nothing there, and that's where we put it in. If we just want to do a lookup, then we would just be looking for something here. The example was looking for hello. If we were looking for hello, we start at the root. Hello would be to the left of. So we're looking at and. Hello would be to the right of and. Looking at ball, go to the right of ball. Hello would be to the right of fast. There's nothing there. All right, let's get into the code now. See how far we can get. We may need 2 videos for this. This is in data structures, and we have a start here in bst.h and bst.c. So here we have bst.h. This is the node which has data. In our example, we're using the word, and it has a left and a right pointer, which the type of those is the node itself and then the star. Alright, these are some of the functions that we'll need. I'll just put little comments for what they are. So this is allocating memory for new node, initialize to nulls mostly. Okay, so that will be when we create a new one. This would be for freeing memory when delete. Lookup should probably search for word, return the node. Insert, we would create a new node, put it into the tree, and then we have some delete possibilities that we'll get to. Move from tree, and we would also have the one for printing the tree. I'm going to add in we'll leave it like this. Okay, so bst.c, we got to start on the lookup, which it should look like if you read the code what is described here. And in pictures, you have something that you want to look for, you check the root, you either go left or right, or you find it. Eventually you might get to a null. Let's check the code. So here we have root. If the root is null or the word is null, we're not going to find it, so we return null just as a status to say it's not there. Otherwise, we have a pointer p that keeps track of what we're looking at. We start at the root. As long as p is not null, we check the word that we're looking for against the word that's in the data of the node we're looking at. If this here, so this is str compared to something like word minus p data w. Okay, so if it's negative, then that's like saying that the word is smaller than what we're looking at, which means we need to go to the left. If it's bigger, we need to go to the right. If it's equal to 0, we found it. Alright, so that's a lookup. I'm going to go ahead and put in here that we need to include bst.h. Alright, so let's do, so we have started code for insert here. So what we've done for insert is first we create a new node, and what do we do for that? First we need to allocate the memory for the word t. So this is just a string, but we need to make the word t data structure. So this all initializes that, and that's from the word project. If you need to look at that, you can go back and look at the when we created the words.h and the words.c. Alright, so if you want to pause and go look at that, you can, but it's not absolutely necessary. So this is the part where so this is create and init a word t stuff. Okay, so this is where we create and init our BST node. Alright, so now we need to find out where do we put this. Okay, so we have to do this. We're either going to do basically copy and paste this again about looking left, looking right, or we modify this algorithm to do what we need. So let me pause for a second and think. Okay, I think we will go ahead and copy paste this, and then maybe we'll come back later and combine this. But what we want to do is basically find where this is supposed to go, but then put it in the right place. So something to keep in mind here is that the type that we have here on the parameter is a star, that's a pointer to a pointer. The reason for that is if we're trying to do an insert and there is nothing yet. So somebody has to be the first node. In this one, the first node created was of. Before that, there was nothing, and root just was a null pointer. And if we're doing an insert and it's the first one, then we need to send back a pointer, so we need to change this. And so we actually need a pointer to that. I'll put that in first. That's an easier case. So if we're looking at star root here is the pointer. If this is null, then this is the first node. And this is pretty easy actually, because we have we've created our BST node. There, we did a pointer to the data. So we created the data here, the word t. This pp is a node, so it's sort of sitting off here like this thing here, and it has null pointers coming off of it because that's what we did in the mk node, BST. First the data and the left and the right are all null pointers, and then after we get that back we put the data to be this word here. Alright, and then that would be fine. This is ready to be the root node. So all we'd have to do is say star root equals pp. And that's it. We would then return pp. This is supposed to return the node that was just inserted, just in case we might need it. Alright. So that's that case. And that means that if we're here, we know that star root is not equal to null, which is good. We can go ahead and use it. We don't need to check for this root equal null business. If we want to be paranoid, we could check up here if word is null. I don't really have a strong opinion about that. We can make sure the rest of the code never tries to insert a null word. We'll just leave that out for now. Okay, so we're going to do this. Okay, we're going to do this where we do the lookup. We're going to start at the root. Here we have the parameter is the star. So we need the star root. And we can look at this whole business. So what we would like to do is get to the point. So we do want to keep going. Actually, this should never happen to where it's 0. That would be the case that we already have something in here. Let's say that we tried to insert the word ball. There's already a ball there. So then what are we supposed to do? Either we would increase the count, or we can have 2 nodes with the same value, but then the next one goes just to the left or just to the right. Or we just assume it doesn't happen. I'm going to assume here that it doesn't happen, and we can always modify that for a homework assignment. I'll say note, we assume word is not already in the binary search tree. Okay, so in particular, I'll just put here error insert BST value already in BST, and then exit. Alright, and then there doesn't really need to be any returning there. Okay, so if that's not the case, then we know if that doesn't ever happen, we didn't find it, we will get to the point here where P is null. Instead of P is null and not found, then P is null. This is where we should insert this new item, PP. So we'd get to the point where if we're inserting cat after fast, we got to here, the P was this pointer. So all we need to do is save the parent as well. So I'm going to do, there's a P, and then we'll do a parent as well, which initially is null. And then whenever we update P, we will update the parent as well. So now we'll say parent equals P. Okay, so parent has the same value as P right here, but now we're going to update P. So then P will be the parent. So we know that when we get into this loop, we know initially P is not null because P starts being the root, and we know the root's not null because if it was, we would have returned. So this parent does get set, and then it gets set, and then this code here always runs, so we advance P, so this parent will be the P, and that's kind of cute that we just have to have one line like that. So P is null, and parent is the node we want to insert into. If we want to, we can save ourselves a little bit of time by keeping a record whether we went to the left or to the right. So I'll do that. I'll say int on left, start off being -1, but then here if I went to the left, I'll say on left equals 1. If I went to the right, I'll say on left equals 0. So that just keeps track of which way we were going. And then when I'm down here, then I want to insert PP into parent, and on left says which side. Okay, so I know that parent, if I was on the left, then really what I want to do is parent left equals PP. Otherwise, parent right equals PP. And at the end, we're supposed to return the pointer because maybe somebody would want to use that. Okay. Alright, so what you want to do right now is take a pause, open up a text editor, and type out or write on a piece of paper or something, what is the basic algorithm for insert, and what are the different cases that we have to worry about. Alright, so do that, take a pause for a second, and then come back. Alright, you're back. Now, the basic steps. We need to create the data itself. So that's this word _t that we're doing that creates the data. We create a node, binary search tree node, and we put the data in there. So together, these parts create a new binary search tree node that has our data. Okay, then we want to find out where to put it. That's our block there. We need to find out where to put it in here. One case is that we're the root node. That's actually pretty easy. If this is the first thing inserted, there it is. Otherwise, we're basically doing a lookup, but we need to keep track of the parent of the current node, because eventually the current node is going to become null, and once the current node becomes null, we can't go backwards on that. We need to save where we came from. So there's the parent. All right, so that's insert. We have lookup and we have insert, which are basically the same, and we should also do a print, and we'll be ready to actually put this in. Print all nodes of the tree. It's not going to print a tree, but I can print the actual data. And I'll print them in increasing order alphabetically. Okay, so your basic algorithm for printing, note this is traversing the tree. So basically what we want to do, we have the root node. We have the root node here. We're going to go through and hit every one of the nodes. So I want to print this part here, but then I also want to go to the left, print that part, go to the left, print that part. All right. This is going to seem maybe like magic the first time you see this, but I'm going to go ahead and put it in there. So if the root is null, then we don't print anything. All right, so otherwise, we're going to print the root's left part, print the root's right part, and we need to print ourselves. So here we want to actually do the data, which we have to go back to the word stuff. Okay, I'll do the word stuff down here. Words, let's see, bst.h. Okay, so the word is in data, so inside of data there's something. And in the words.h, what do we have? We have print word. Okay, so I want to print word, and the thing I'm going to print is that, and I'm going to print to, I guess I'll do the same thing here, file star f, I'll print to f. So that could be std out, or it could be something else. So I'll update my Alright, and that is it. So we're going to print everything to the right, sorry, to the left, print me, print everything to the right. And you notice that this is a recursive function. That means it's a function that calls itself. And you should recall that for recursive functions, there's always one thing that you definitely need to have, and that's a base case. The base case is where you don't do a recursive call. So eventually the recursion needs to stop. And I'll make a note. I want to slow down here, but I'll make a note. Recursive functions, base case for the notes. All right. So that might work. And it sort of seems like magic that you're printing the whole tree just by doing these little 4 lines of code. And let's see if it seems like they'll do it in the right order. I wanted to print in increasing order, so in this tree I would want to print all first. Is that what happens? Root initially would be the of. We go in here and we would do the recursive call. Root left is and. So then we'd be doing the print binary search tree with and. It comes in, its left is all. So we'd be in binary search tree with all. The left of all is null, so it won't do anything, and then we would print all. Okay. That is fine. Now let's see if we can use this. So we're going to make a copy of simple.c, and now this is going to be simple, we'll just call it BST. So we're going to use this binary search tree instead of what we had before. So what we had before was a max words with a words array and a num words lookup in that array. We're not going to use insert. We're not going to use print. We're not going to use. So that was all having to do with storing things in an array, and then we're just left with the part that scans through the file. So then here we do need to have a root pointer. So what do we have? BST node underscore t star root. Initially we'll set that equal to null. So this is initialize the BST. All we have to do is set our root pointer to be null. Alright, then here we already have a comment here that says we're going to do a lookup BST and root, and we can check to make sure that's the proper method. So we have lookup root and with a character, and it returns a pointer. So instead of I here, there should be BST node t star. Normally we'd use p for pointer. Okay, so if p, now I want to do something, so here's a question for you. Based on the lookup and what it's supposed to do, I can go back over here and let's see. So here's lookup. If the word is present, if this is not the first time we've seen it, what's the condition here? Before we had a condition on I, now we have a condition on P. So pause. Alright, and now the condition is if P is not equal to null. So this lookup here returns null if it's not found. If it is found, it returns a pointer. So if it's not null, then we want to increase word, and we need to go over to the words.h to see this increase word, what is its parameter. So here's increase word, and we're supposed to give it a pointer to a w. And we have a pointer to a BST node. So we need to go back over to bst.h. BST node has a parameter called, or a member called data. So we're either going to do p.data or p arrow data. Which one? It's the arrow because p is a pointer. The star. So we'd always need to do star p if we want to take the value. It would be star p.data but you need parentheses to do that to make it work right. That is correct. You take the value of the thing that it's pointing to and then look at the data parameter, but that's too much to type, so we do this. All right, that's if it's present. If it's not present, then we want to do insert BST, and here is the values for that. So we have to give a address of the root pointer, and that's that. There's a few functions here in the bst.h that I haven't created yet, so we haven't done delete and we haven't done free. We'll leave those. So right now we're just going to try to compile this. We'll add a line to our makefile. So this will be BST, we'll do words.c, and also bst.c, and we have simple BST, and we'll call it SB. Alright, make BST. It's not surprising that there are errors. I will make you watch this just because we're going to change things. So line 22, right, there's nothing called BST node. We need to have the underscore T. All right. This was in the print, so we have BST node underscore T. Let's go ahead and do that again. This is on bst.c line 35. If you want, you can pause and see if you know what the errors are here. I think I don't remember exactly. Let's try this. Right. This is the usual way to do this. All right, let's ignore that warning. It's okay for now. This should be Word. Yeah, some of these things you probably noticed while I was typing. Okay. Duplicate P. Did we have a P up here? That is the new one. So we should have some other name. This is a word T. Why don't we call it W? We're not using W there. I think that's the last time that that one is used. Print BST. Right, recursive call passes the file pointer along. Looks like MK node BST. Are we missing something? Let's go ahead and try to compile again. There's that warning that I'm ignoring. Right, we are supposed to return the pointer. That's definitely a problem. And then we're over into simple BST. Alright, we just have the pointer, so let's do BST. Let's see, what is it called? It's going to be called SB, and say we just run it on words.c. We could test this against the S was there, and we should get the same counts. This was just giving the first 5, so if we go up to include, see if we get 5 for that. There's a 5. This is printing them all, and it's printing them in increasing alphabetical order. So we should do a test on a larger file, so we can do the Shakespeare one. The collected works of Shakespeare. I don't want to print that to the screen. And that's much faster, which was kind of the point of doing a binary search tree. So we could run the time on that. So that took 0.27 seconds. And let's check the output. What are these spaces? The 27,000 times. We could check that against the other file. Okay, so there's more work to be done. We haven't done delete. We haven't done free. We could make this print function so that it maybe prints the top words, or to look up a particular word or something like that. Those will be good homework assignments. Right. So just to emphasize, maybe we'll come back and look at the running time in another video, because I think this is about it. So the running time here for all of these operations is order the height of the tree, and this is the whole point of doing binary search trees, because the code is definitely more complicated. If you look at the code, so this is 46 lines of code. No, not that one. bst.c. So that's 110 lines of code, and we still need to do free and delete. If we look at just the same functions for simple, I don't know. That's like 45 lines, so half as much code. But the binary search tree is much faster because the height of the tree is order log n. So we just should put, for example, if n is 1 million, log base 2 of n is about 20. So an operation that with the unordered array, so there's an unsorted array, the basic operations were order n linear time. So if n is 1,000,000, that would take 1,000,000 steps roughly. Now for us, it's taking 20, which is much better. All right, that'll be it. Have fun.